What's up, everybody? So, it's been a while. It's been a few weeks. Um, but I'm back today. We're gonna continue on in the series, and I'm gonna do clip next. So, OpenAI's clip, which is a image text. It's a multimodal transformer. It's a multimodal model that can give a similarity score between images and captions of those images. And we're going to use that in Stable Diffusion in SDXL in order to condition the diffusion process. So I'm going to do the clip architecture on my iPad and show you the objective function in math, the math note in using math notation, and then in a separate video, I'm gonna code it from scratch in PyTorch. And I'm gonna redo the transformer. I'm gonna redraw and recode the transformer architecture because one, it's fun, and I think it'll be a little bit easier to explain now that I can use my iPad and hook it up properly to record. So yeah, a brief note on the different modalities of expression, the different modalities of machine learning and how you can express yourself. The three modalities are code, math notation, and diagrams. And I just want to make a quick note on this. They're not transferable, right? Like, just because you're good at math notation doesn't mean you're going to be good at coding. Just because you're good at coding doesn't mean you're going to be good at math notation. And just because, right? So they're sort of, I wouldn't say they're mutually exclusive, right? Like, building skill in one area there is transference, but not in the way that you're thinking. Like, there are different neural centers in your brain. I mean, I don't know the actual neuroscience, but I mean, you don't need to in order to understand that there are different neurons in your brain, right? Like, all you need to do is, become good at coding and then try to write some math, and you'll be like, wait, I'm simply just doing the discrete mathematics. I'm writing, writing this algorithm. I don't know, writing using set notation or using series notation to describe, or summation notation to describe what's happening, but you're going to find you get stuck if you don't practice it. Now, some of you might think, well, all I need to do is learn how to code. It depends on what level you want to move to. I'm a first principles guy. I'm a master guy. You know what I mean? I like mastery and I like first principle. I want mastery of first principles in everything that I touch. That's just how I operate. If I'm assuming the people that are drawn to this channel are also going to be probably operating on that wavelength, given the long form of the videos and just the nature of what I'm doing. If that's the case, you need to master all three modalities. And so what that means is working with the three modalities whenever you get the chance. The reason why it's important, it's not just because these modalities exist and that's the convention in the field. They're working your brain, they're working different parts of your brain, like I said, which helps you reason about the problem differently. And it helps you reason as a scientist and as an engineer more completely, more dexterously, right? Like, math notation is it forces so math notation forces you can be kind of hand wavy with diagrams, but you can't be as hand wavy with math notation. Like, and then moving down the spectrum even more, you can't be hand wavy at all with coding, right? Math notation Also, when it comes to being able to manipulate things, coding is good once you sort of have your model objective built, and then you can code it out, right? You have your model objective derived, you've created the diagrams, and then you can code it out. If you want to sort of manipulate the foundations of your objective, it helps to do it in math notation, because you can. My point is that doing things in the different modalities will help you see things that you couldn't see if you're only embedded in one modality. That's my point, right? Like, if you want to reason, if you're stuck on a problem and you want to see something differently, then change the math notation or switch to diagrams, right? And it'll help you reason about the problem differently. So yeah, that's the main point of what I'm trying to say. I don't know. Maybe I'll dig into this in a separate video sometime. But for now, let's just leave it there. So, let's start off. I'm gonna derive the objective function, and then I'm gonna diagram out transformers and the clip architecture, and then we'll end the video, and then I'll code it up in PyTorch. Clip. So I'm gonna write out the data set first, and then I'll briefly show the architecture of the model, and then we'll go back to the objective function, and then we'll go into the details of the architecture. It'll make more sense this way. So remember, clip is a multimodal image text model that gives you a similarity score between an image and a text description of that image. So let X, so it's going to be capital X, let X and Y be an image and text matrix respectively, such that little x sub I, little y, let's look at J, sub I, where the data set has endpoints, so from I equals 1 to n, are image caption pairs. Where X sub I is in R, so it's an image channel, which is going to be 3, height and width, and YI, it's a tokenized string. So it's going to be a sentence that's tokenized using the tokenizer, right? We're going to say it's an RL. So it's going to be a list of tokens. A list of token IDs. So, right, okay. So this is so let's say we have an image, an RGB image of a dog that says wolf. And then our text description is an image of a dog saying wolf. So, right. So what we want is a model that can give us a similarity score between this image and this text, right? So I'm just going to sketch this model really quickly. We're going to have so okay. So we have, so basically we're going to create embeddings. We're going to create an embedding out of this and an embedding out of this. And then we're going to feed it to we're going to feed the image to an image transformer and this to a text transformer. And then we're going to project, there's a linear projection layer here and a linear projection layer here that's projecting these, the output of both of these to the same embedding space. And then we're going to take a similarity score on those embeddings, okay? That's our model. It's simple, but it's complex. Simple, but complex. Well, the idea is simple, the architecture is very complex, and the loss function is also complex. So now that you, so this is what we want. This is what we want. So now that you see this general idea, put this here in the corner. All right, so we have these two, this is our image matrix, this is our caption, our text matrix, such that if we use the same index into the matrix, we grab index, you know, let's say this is 1, we grab index 1 here and index 1 here, we get a matching image caption pair. So we get the exact, right, this is our training data, we get, you know, we get an image of a dog saying wolf, and we get the caption that describes it, right? So that's our training data. Now, what's our loss function going to be? The idea is we want to maximize the similarity score between, so what we're going to do is we're going to take a batch of data, a batch of image caption pairs, and we are going to, so we're going to randomly sample image caption pairs. We want to maximize the similarity between the positive image caption pair, and we want to minimize the similarity between you know, this image and then the other caption, the other randomly sampled captions in the batch. All right, so we want an objective function that can maximize the positives, and so maximize the positives and then also maximize the margin between the negatives. Another way of saying that is maximize the positives and maximize the similarity score between the positives and minimize the similarity score between the negatives. So that's, we're going to achieve that with the InfoNCE loss. Or it's also called contrastive loss. Okay. So let's continue on with our math notation. So we have X and Y, and then we're going to call this V. We're going to call this vision encoder V, and this text encoder T. And then this linear projection is going to be represented by the matrix WV. This is going to be capital W sub T. And yes, okay, so we're going to say being slightly hand wavy here. Well, yeah. We're going to say that V, right, is a function that takes in an image represented by a channel height and width and outputs a vector here. And T is a function that takes in a list of tokens, a vector of tokens, and outputs an embedding here. So obviously this image is going to have to get, you know, converted into a format that the transformer understands, right? But we'll get to that. So for right now, we'll just leave it a black box. So we'll say E sub I, right? So for right now, we're gonna assume that the index for the image in the caption is the same. It's sub I, just to indicate a matching pair. So E sub I is equal to W V X sub I. And then we need one more additional step called normalize. It's unit normalization. So, and then E hat sub I is equal to, so that's your normalized vector is equal to the norm of E. So E divided by E sub I divided by the norm of E, right? So basic vector math. So, and then little W sub T is going to be equal to capital W T text transformer on YI Okay, so we send the image through the vision encoder, which gives us a vector that we send through a linear layer, multiplying it by a matrix. And then we get E, and then we normalize by the norm of E, the magnitude of E, to get the normalized vector E hat. And we do the same thing with our corresponding caption. Now that we have that, how do we calculate this contrastive loss, right? So for prediction, we're just going to take cosine similarity, right? But when we're training the model, we need this contrastive loss function. So we're going to let capital S I J equal cosine similarity between E hat sub I W hat sub J times, and we're gonna multiply by a logit. We're gonna scale the logits by basically just a temperature. We're gonna scale all the values in the matrix by a value, and that's gonna determine the peakness of your it's gonna determine the pointedness, the peakness of your softmax distribution. So this is going to be a learnable parameter. Tau is going to be a learnable parameter. So let capital S ij, right, be a similarity matrix. Where tau is a learnable temperature. So now we're indexing, I and j indexes a single point on this matrix, a single element of the matrix, okay? So now we need to define, I'm going to define two terms first, and then it'll come together in a second. So P I j is going to be equal to, so this is, we're going to calculate our softmax distribution now. So exponent, so Euler's number S, so this is normalizing I, K, okay, so we're defining a conditional probability. So let me draw this first, actually. So we're indexing into any point so this is indexing into a point in the matrix, and you know, to determine, so this is an image. Let's do this. I'm going to keep the J's as text and the I's as images. So we're going to do, oh, right. That's just follows the notation. Yeah, that follows the notation that I'm doing here. Image, text. So the J's are text and the I's are images. Okay, so the rows are images, columns are text in the similarity matrix. And then this is going to be from 1 to B. So right now so I should have made that clear before. Well, actually, I'll say it now. So right now we've calculated this similarity score over let S sub ij be a similarity matrix for a batch B equals batch size for a batch of image caption pairs. Where tau is a learnable temperature. Okay, so we're on the batch level now, and this matrix is 0 to B, where images are indexed by the rows and texts are indexed by the columns. So now, given an image, we want a distribution over texts, J. So given an image I, so we're indexing into this matrix here. Like, so let's just say that I and J are such that we're indexing right here. We want to know the probability of J, the probability of this text given I. So given an image, we want a distribution over J. So we calculate that softmax by dividing the value here by we're essentially normalizing over the column values, over the text, over each text in this row. So we're iterating over the values in the column, and we're normalizing, which is normalizing row-wise, right? And so if we were to index, let's say here, we would normalize there. If we were to index here, we'd normalize this row, like assuming these are rows. If we were to index here, right, we'd normalize that way. So this way, so essentially and you'll see why this makes sense in a second. So now we're going to define Qij. So we're going to define another conditional distribution, 1 to B, sorry, K, this is K equals 1. S, K, J, and this is S, I, J. I guess I didn't have that K here. I kind of, right, so you can see how K is the varying element, it's the column. So the columns are varying. And in this case, in the case here, we're going to normalize sloppy. Normalize column wise. Oh, I just realized it would be much better if I had done it horizontally. Sorry, folks. I'm not redoing this video though. We're just gonna have to. It's gonna have to make it work. So, yeah. Okay. Well, keep going. Okay. So here, the rows are varying, right? So when we're looking at this value, boom, the denominator means we're gonna normalize, right? K, we're gonna normalize column-wise, which means the row is what we're iterating over. So for given a text J, we want a distribution over images. Given a text J, we want a distribution over the images. Given an image I, we want a distribution over the text, over the captions. Now, why is this important? Let's copy this. Oh. Let's make it smaller. Now that the view is different. So now let okay, so I just wanted to make a quick note. So I had to re-record this part because I made a mistake that's pretty important. Very, very simple, but there's supposed to be a negative here. Because this is cross entropy, there's supposed to be a negative. And I forgot that. Because all your probabilities are going to end up being negative, and you need to multiply them by a negative so the value is positive, which is what you're going to minimize the objective function. So, yeah, that's all I wanted to say. So I guess just you'll see the rest of the content, and it will not have a negative here, but just know that there's supposed to be a negative here. Loss image to text, I to T, is going to be, so now we're going to define our loss. It's going to be, so for this batch, remember, this is on a batch level. P, I, some P, I, given I, no. So this is cross entropy. So now we're defining our cross entropy loss. Log P, I, given I, and then text to image equals log Q you know what, how about we move away from I and J just to make it, let's just use something completely different. Let's use K. So we'll just so you know, it's the same index. To be K to be. So this is image, text, image, text. So, okay, we'll draw one more thing. So what we're doing, normalize. Normalize. So okay, so you can see the indices are matching. So we have the probability of a text given an image, which means that we're normalizing in this direction for all the rows, right? And the indices are matching, so we're summing along the diagonals. So these are positive. So what we're doing is we're summing all the positive pairs in our batch. We're summing all the positive image caption pairs in our batch, but the values are normalized by the negative text, the negative text values, right? So the values of the text that make this image text, that make the image text pair negative. So this image text pair is the positive one, the rest are the negative. The rest of the texts in this column are negative, and we're doing that for every single value in the summation is a positive image caption pair that's normalized by the remaining negative samples in the batch. It's genius, really. And then for this side, we just flip it, right? We get the same positive image caption pairs, but we're normalizing by the negative images in the batch. It's brilliant. It's genius. These simple things that sometimes people don't. I think sometimes with machine learning or with math, people like they want to seem so impressive for like explaining something that they don't call out how genius something is, you know. And also, like, when you're doing complex things so often, things fail to impress you, you know what I mean? And you forget how impressive something like this actually is. So then they say loss clip is equal to image to text plus text to image divided by 2. So it's the average between these two losses. And this is what you backpropagate on. This is what you backpropagate on. So this will. So you need to. I explained it all, right? So everything is here for you to understand it, but it might take a second to click to see why this does what I said in the beginning, which is it maximizes the similarity score between the positives, and it minimizes the similarity score between the negatives, and it does this batch-wise, right? So you're gonna collate batches, and you're gonna calculate this loss. So I guess, right? Like, so you're gonna, sum up all the losses across all batches, right? So this is the loss for a batch, for a single batch, right? So yeah, that's the loss function. So just one more time all the way through, we have our vision encoder, our text encoder. We have X and Y are matrices. This is image matrix, caption matrix, such that if we index with the same index, we get matching image caption pairs. So we have an image, and then we have a description of that image. So this is a vision encoder, text encoder. This is a linear layer represented just by a weight matrix. And then we have a normalization operation that happens here, and then a similarity score. So we have vision encoder that takes in, a vision transformer. You could call it an encoder, but it's a vision transformer that takes in X. We multiply it by, we project it into, so this is projecting the outputs into the same embedding space. That's what this linear layer is. It's super necessary to have this. If you don't have it, I guess it's possible that your model could still converge. It's possible, but it'd probably be pretty challenging. So, and then after we project them to the same space, we normalize the vectors. This is for stability, and also, so we don't actually have to calculate cosine directly. We can just take the dot product, because the dot product of normalized of unit normal vectors is the same as cosine. So we define this similarity matrix, and we also divide by a learnable temperature. And we're doing this on a batch level now, right? So we're gonna take batches of this. We're gonna take batches of this data set. This is from 1 to n, but now we're gonna batch this data set. And if this similarity matrix is calculated for a batch, right? So this is 0 to B, and this is 0 to B. So 0 to B images. So it's always going to be image, image, text, text, right? So this is, we have an image vector here, image vector here, image vector here, text vector, right? So we're taking the dot product. It's just like attention, just like it happens in attention. So now we define these conditional probability distributions, right? So this is the image and this is the text, such that if we want to get, so this is just a softmax distribution. We're calculating a softmax. The only reason I'm doing the notation this way is to show you how when we switch from P to Q, we're switching from normalizing row-wise to normalizing column-wise. And then to actually calculate the loss, so the image to text loss is going to be, we're going to sum along the diagonal. So these are all the positives. These are all the positive samples, the matching samples, the image caption pairs, and it's just normalized by the negative texts, the negative captions along the column. And this is all, again, it's all the positive image caption pairs, just normalized by the negative images along the rows. And then we take the average of that, and we'll just sum all those averages. We'll sum all the losses for the batch, and then we'll sum all the losses for the batch, or we can actually just average, and then we'll back propagate on that average. And so, okay, let's keep going. Let's actually diagram this out. So I wanted to talk about transformers again for some of you that are new. I don't think I'm going to do this often where I review things like fully, but I just feel like doing it now. I don't have any other reason other than I feel like practicing it. So let's just do it. So what I'm gonna do is I'm gonna expand right now. I'm gonna expand this to show you what we're actually gonna code. So let's do patch embedding. So patch embedding. In these diagrams, I'm actually going to create classes. These diagrams will map one-to-one to classes that I'm going to create in PyTorch modules. So patch embedding is, so we need to take this image. Let's copy this. So we need to take this image before we send it into the encoder, we need to create a patch embedding out of it, right? So if you recall, a patch embedding basically takes a 3-channel image and then it turns it into, right, a tensor where each column is a d-dimensional embedding. So basically, each column is a d-dimensional embedding that represents your patches. So this will be 0 to p. So if you have an image, say this is your image, you're gonna basically have patches. Right, so if this is 5 patches here, 4 patches here, you'll have a total of 20 patches. So this will be 0 to 20. And then each patch, we're gonna create a vector out of each patch. And that's how we're gonna represent the image. So it's gonna be, the number of vectors is gonna be P, and then each vector is gonna have, a D dimension. It's the same thing that we're doing with tokens, right? Like if each of these are tokens, we turn the tokens into embeddings by going into a lookup table and grabbing the embeddings. So the way we're going to do this is, I think I have space to do it here. The way we're going to do this, so I'm going to do some kind of like diagram / pseudocode. So the way we're going to do this is, you know what? Okay. Before I do the diagram, I'll just do a little bit more kind of pseudocode / notation. So I'll just sort of keep going along with the explanation. So we're going to have we're going to do this. So before I implemented this kind of from scratch using fold in one of my previous videos, it's easier to use a convolutional layer. That was just for educational purposes. So we're going to say in channels is going to be 3, right? RGB. Out channels is going to be, we'll say D. And then, so that's going to be, so D is, okay, well, let's just keep going. Kernel size is going to be let's call it, let's say PS for patch size. And then stride is going to be PS also. Okay. PS equals patch size. So D is the size of this, 0 to D for all of these. And then P is going to be your number of patches. Patch size is literally this. The size of this kernel, the kernel is patch size. So let's say it's 3 by 3 pixels by 3 pixels. So let's say patch size is 3. We're gonna extract a 3 by 3 patch. And then we're gonna stride. The stride is gonna be equal to the patch size. So there's gonna be no overlapping patches. We're gonna just extract patches like this. So with that being said, So now P is going to be equal to H divided by patch size times width divided by patch size, right? So the height divided by the patch size is going to give you the number of patches and the height. So in this case, it's 4. The width divided by patch size is going to be 5 here, right? You multiply those together and you get 20. You get 20 patches. You get P. So I think we have enough here to write out patch embedding. So, okay. So now let's, okay. So patch embedding is, let's keep this. So X is going to go into conv 2D. This is going to give us a tensor that's, it goes from channel height width to, let's just assume the batch size is 1 for now. Will that work for my example? It should. Actually, I'll just make the batch size implicit. You know what? Fuck it. We'll just make it explicit. It's just going to be B. So this is going to give us, this is going to give us B, D, right? So we're saying, let's write this out. And then height divided by patch size, width divided by patch size. Okay, so remember, just the rules of convolutional layer. We go from out is always going to be, I can't go across the page for some reason. Out is always going to be that, and then, right, just doing the convolutional tensor math, the dimensions of your image are going to be height divided by patch size and width divided by patch size. And then what we want is a vector, right? We want this vector, right? So we want B, P, and then what do we want to call? We want B, P, and D. That's what we want. We want a tensor of batch, and then that's essentially we want number of patches, and then we want the patch embeddings, right? That's what we want. We want a patch embedding. This is a patch embedding. This is the number of patches, and this is the size, and these are the embeddings for each patch, right? Right now we have B, D, this, but remember P is this, okay? So we just need to do some tensor operations. We go, I'll spell this out for you. Flatten, starting at second. This is going to give us B, D, P, I need to make sure this fits. P equals H PS times width divided by PS, right? So we're flattening starting here. So this is gonna flatten out. If you don't know the flatten operation, I've discussed it in plenty of my videos, so that's a fundamental PyTorch thing, so you should know that by now. flatten just it right, it denests. Whenever you denest, you're doing a combination operation. So you're just multiplying by whatever list is nested under that level, right? So now we do. So now we have B by D by P. We have a BDP dimensional tensor. We're going to transpose, right? We want BPD, so we just transpose to 2, 1. And this gives us P D. Gonna make this fit. Okay. Now I have BPD. Yeah, that's, oh, right. So we have the patch embedding, but I'm gonna make a class that does a little bit more. So now we need to, if you remember in my previous video on vision transformers, now we need to add a class token. Okay, so maybe we have some space up here. I'll just talk about the class token. Basically, we have, maybe we have some space here. Let's, so now we need to add a class token that's going to aggregate the information. It's gonna be a represented. It's gonna contain the aggregated information for the entire image. So you could almost think of it as an average, but it's not an average. It's not an average. That's not a good word to use. You can think of it like an average. It's an aggregate. It's a very sophisticated aggregate. It's a learnable embedding that's of size D, and it's going to aggregate the information, and it does it structurally. It does it because we're going to code the model and the loss function such that it has to put all the information into this embedding. Maybe that won't be clear yet until I write the code, because you'll see how essentially I'm just returning, I'm only returning this, and I'm calculating the loss on this embedding. I mean, I'm using this to calculate the loss. So when I back propagate, the gradients will flow through this. The gradients will flow through this embedding. We'll come back to that. So, but for now, just a few other points. This class token is 1, 1, 1, D. So, and it's a broadcast. It's a broadcast. You can consider it a broadcast variable. That means it's one learnable parameter, but we're going to distribute it to all elements in the batch. So maybe let's try to make that a bit clearer. I want to go into these details because these are the details that other people don't explain in their videos, and like you really want to make you want these things to be clear. Otherwise, you don't want to hand wave things. You know, that's kind of the point in the videos I'm trying to make. Is like no hand waving. You know what I mean? You don't understand something until you fucking understand the whole thing. Period. And I don't want anybody to tell you differently. So let's put this here, and this is going to go here. So this is our batch, right? So in our batch, we created a bunch of patch embeddings, right? 0, 1, 1 to B. This is our batch. This is a broadcast variable, which means we initialize it as a parameter. It's a single parameter. Single parameter that's shared across the entire batch. It's a single parameter that's shared across the entire batch. And we just do a little bit of, PyTorch knows how to handle this. As long as we code it properly, PyTorch knows how to handle this. Okay, so back to our patch embedding module. So we've extracted patches using a convolutional layer. Then we flatten, starting at the second index, to multiply the number of patches in the height times the number of patches in the width to get the total number of patches, P. And then we transpose. So now we have this vector. We have P along here, and we have a d-dimensional vector. And now we're going to add the class token to each element in the batch. We're going to broadcast it. And this gives us B, P plus 1, P plus 1, D. Oh, it's sloppy. Just gonna expand it. B, P plus 1, D. And then, just like any other encoder, we need to add positional embeddings. So make that a light color just to kind of illustrate the point. Just kind of adding this on. It's plus. Boom. That's your positional embedding. And then, so positional embeddings are, we're gonna broadcast those across the batch as well, right? So positional embeddings are shared across all elements in the batch. Right, obviously we're not gonna create separate positional embeddings, but well, it's not obvious. I don't like to say obviously. These things are not obvious if it's your first time. It's the furthest thing from obvious when it's your first time. Anyways, and then we're done. So let's go here. Boom. All right, so let's see if we can finish this up. All right, so we have a patch embedding. Now let's get an attention head. I'm going to move through these a little bit more quickly because I've done them before. So X, we're going to have mask, query times key, K transpose, K transpose divided by the square root of H, which is your head size. And this is an attention mask. Okay, so we don't want to calculate attention on the padding. So like if your max token size is 100, not all of your tokens in the batch are going to be that length, right? There's a chance they won't. There's a chance some of them will be 50 tokens. So then you pad the rest, right? But you don't want to calculate, you don't want to waste compute on, you don't want to compute attention on the pads, right? On the padding. Not that it'll mess up your calculations. It's just wasted. It'll slow your training down significantly, especially when you start to scale up. So basically, this attention mask is going to set padding values to a very large negative number, so that when you divide by that, it's going to be a large exponent. So it's going to be, when you divide, it's 1 over a large number, it goes to 0. H equals, so H equals head size, which equals D, the embedding dimension, divided by the number of heads, which I haven't explained yet. But I will when I get to multi-head attention. I think I'm going to do multi-head
attention here. So this goes here, and then we're gonna do softmax, and then we're gonna do I think that's it. Softmax, and then we're gonna do so let's say this is, what do we want to call it? Let's say this is A. We're gonna do softmax of A, and then we're gonna do A equals softmax of A, and then we're gonna do A times the values. And then we're gonna do dropout, and then we get our result. This is matrix multiplication, and then dropout, that gives us X. Yeah, so this is our attention head. Pretty sure that's right. Okay, so now let's do multi-head attention. So multi-head attention is going to be, so we have X, and then we're going to have an attention head shoot. Oh. Okay, so we're going to split X. We're going to split X on the D dimension, so on the last dimension, right? The embedding dimension across heads. So we're going to split that embedding up. We're going to send it to different heads to calculate different attentions, and then we're going to recombine right? We're going to recombine. And multi-head attention, where do we go after that? This is not a I mean, this is a concatenation operation. So I'm going to say cat for concatenate. So we concatenate, and then what do we do? We concatenate, oh, and then we have a linear projection. Project project, and then drop out. Yeah. Now, transformer block. So we're almost done. Transformer block. Let's bring this down. Is going to be X multi-head attention to we do normalize first. So the original Transformers paper has normalized post normalization as a post. We're going to do it as a pre. So layer norm, multi-head attention, layer norm, and then we have the feed forward. We have a projection layer. This is going to project it up in dimensional size. And then we have gel U. Let's just put these close together. And then a linear down. We're going to project it back down. So this is just adding more expressiveness to the model. It's just the paper and the experiments they did, they found that this is the ideal, the optimal architecture. You project it up, you add dimensions, then you bring it back down to the same, to what it was before, and then drop out. Drop out. And then you're also doing residual skip connections. So here, here, and then let's move this down a bit here. I think it's drop out and then yeah. Layer norm, and then X plus multi-head attention, and then X is layer norm of that X, and then X plus the feed forward. So the dropout happens first. Yeah. This is how it works in attention. This is your standard attention straight from the paper. Yes, if you want to be a master, you should know how to do it from your head like I'm doing it. I said it. I don't care what anyone else says. Do you want to be a beast or not? I mean, you know, I just think about jujitsu. You know, I do ML just like I do jujitsu. You know what I mean? You gotta fucking know your shit. You can't be live rolling, you know what I'm saying? It's like, how do you do that? Like asking a fucking, you know what I'm saying? Like, hey, how do you do the armbar again? Nah, it's not how it works. Know your shit. I mean, there's wiggle room, of course, you know what I mean? But you get my point. Just know your shit. Know your shit. especially the foundational stuff. Like other things, like sure, swim transformer or whatever, okay, but like something like a transformer, something foundational like ResNet, like that stuff, you gotta just know. It takes time though. It takes practice. So okay, we have a transformer block that's made up of these previous blocks, right? And now yeah, yeah, now let's okay, yeah, let's just to save some space, I'll do vision transformer. It's going to be patch embedding, and then transformer block. Yeah, you're going to have n number let's say times depth. That's going to be a hyperparameter. And then you're going to have a layer norm. That's x. Okay, cool. Now we need well, now we have text. Text transformer. Should have just. All right. Text transformer. So for the text transformer, we're getting in a list of token IDs. So we're going to send that list of token IDs, which is X, through, we're going to do the embedding lookup table, right? And then we're going to add the positional embeddings. Positional embeddings. Yeah, that's it. It's not filling the shape, and that's really annoying me. Damn it. Okay. Oh, fantastic. Okay. All right. Okay. We have our text transformer. We have our vision transformer. So now we'll do clip. Yeah, you know what? How about we just, oh, let's go here. All right. So now, so this is clip. Image. Caption. We're gonna have to bring this down. Clip. Freaking wobbly desk. Now we project to the same embedding space. Unit, norm, unit, norm. Oh. And then similarity score. Boom. 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 That's our prediction. This is a clip. This is our clip model. This is our clip model. We're done. Let's see. Let me just switch into this view. I'll switch back. So let's do a quick review. For math notation, I've already explained most of that. The only major takeaways here is that, remember, contrastive loss is maximizing the similarity scores between the positives, which are on the diagonal, and it's minimizing the similarity score between the negatives, which is captured by the normalization that's happening. And then we need to normalize from two different perspectives. From the image, we need to condition on the image, normalize over text, and then we need to condition on the text and normalize over images. One normalization happens this way, one normalization happens this way. Then we add the two losses for that batch. We average the two losses for that batch, and then we can just take the average across all batches. Patch embedding, we are extracting patches from an image, and then we're going to create an embedding for each patch. So we extract the patches, P patches, and create embeddings. And we're going to do that using a convolutional layer, where the kernel side, where we have number of channels in the output is going to be the size of the embeddings. And then we're going to extract patches using a kernel of size PS, patch size, and then we're going to stride by the same amount. And then we essentially just need to flatten and transpose, and then we'll get a B by P by D vector. And then we add on the class token as a broadcast variable. And then we add the positional embedding to each of these, another broadcast variable. Now we're going to standard attention. We have our attention head. We're calculating attention here. One thing to note is that the head size is determined by D divided by the number of heads. So the number of heads is here. D divided by the number of heads, and then we use the head size to divide here. Instead of just like in the paper, you'll see D. It's actually not right. It's only D if you have one attention head. Another notable thing is the attention mask, that's where we don't want to do any extra computation in the attention mechanism when we're training. So we just want to make sure that we set added values to a large negative exponent, so that it's 1 divided by a large, e raised to a large, it's 1 divided by e raised to a large number when you're calculating the softmax, which will make those attention values 0. Multi-head attention, you're just, like I said, you're just splitting your embeddings, and then you're calculating attention on each of them, and you're combining the learnings with concatenation. And then in order for the learnings to be combined properly, you can't just concatenate them, otherwise it's just like this sequential, you need to actually project them back into the embedding space, and that embedding space is something that the model is going to learn through back propagation. Transformer block, multi-head attention, linear layer, scaling up, scaling back down, and then skip connections. Right now we can actually create our transformers. So we have our vision transformer, patch embedding, multiple transformer blocks, layer norm. Caption is embedding lookup table, positional embeddings, transformer blocks, layer norm. And then we're going to project. We have our projection layer, so we project both embeddings that come out of here into the same space. We're projecting them into the same learnable space. And then we do unit norm, and we calculate a similarity just by doing a dot product. We don't need cosine because we don't actually need cosine because we've taken the unit norm, so we can just take the dot product. It's the same as cosine similarity. That's our prediction. Boom. So next video, that was a long video. If you stuck with it, watch certain parts multiple times if you need to. I hope you hope you got something from it. So next video I think will be shorter. I'm gonna code everything from scratch again, starting with the transformer, and I'm gonna build clip from scratch. I wasn't able to train. I did a training run, and I'll show you the results of the training one. So I just wanted to record the final part just for clarity. So I wanted to mention that the reason why clip didn't converge is because transformers are data hungry, as I mentioned in my previous videos. They have low inductive bias, which allows them to do really well at modeling complex global dependencies between images and captions, across images and captions. So 30,000 data points in Flickr, the Flickr 30K data set isn't anywhere close to being large enough to model those for the model to learn, for transformers to learn any kind of meaningful global representations, any kind of reasonable representations in general. So now, let's say we use the model like a CNN, which has strong inductive bias, has a strong modeling assumption for local dependencies, then we'd be able to converge to some kind of performance on 30,000 data points. That's plenty of data to converge to some kind of performance, but we wouldn't be able to model global dependencies, which is critical for what Clip is trying to do. It's trying to, just to give you some kind of example, right? Like, if we have an image and we have like a patch here and a patch here, and we have an object A here and object B here, the relationship will change. If object A is here and object B is here, then the relationship will change, right? So there's dependencies between these two objects, and they change based on where these objects are located. And the same thing happens in a sentence. Where a word is in relation to another word in a sentence changes the meaning of the words in the sentence, and then the other words surrounding the word. So that's what I mean. So if we, when you have a data hungry model like transformers, 30,000 data points isn't anywhere close enough. Isn't anywhere to being close enough. You need something more like so Clip is trained on the Lion data set. I think there are different versions of it, but the one it's trained on has like 400 billion data point, either 400 billion tokens or 400 billion data points. It's something insane, and you have to be working at a lab that has tons of money, tons of compute resources. So yeah, anyways, thanks for watching. I think, we're gonna end it here, and then I'm gonna start to code up Clip in PyTorch.